Have you ever stood at the edge of a desert and tried to imagine green fields stretching as far as the eye could see? Most people would call that impossible. Engineers who had never worked in China would call it a fantasy. But China looked at hundreds of millions of hectares of advancing sand, cracked soil, and dying farmland, and made a decision that would reshape the geography of an entire nation. What followed was not a single project. It was a decades-long engineering campaign of such ambition and scale that it changed the way the world thinks about what is possible when engineering meets determination. Canals stretching for hundreds of kilometers, pipeline networks buried beneath desert floors, irrigation systems covering millions of hectares, and a reclamation frontier that is still advancing today. This is the story of how China turned a desert into farmland. This is Quiet Tech Process. China's deserts are not small. The Gobi alone covers over 1.3 million square kilometers across northern China and southern Mongolia. The Taklamakan Desert in Xinjiang stretches across 337,000 square kilometers of interior arid land so extreme that its ancient name translates roughly as the place you enter and do not leave. Together with dozens of smaller desert and semi-arid regions, China's dry territories cover an area larger than the entire nation of India. But the threat was not just the existing desert, it was the process of desertification, the advancing transformation of marginal agricultural land into desert through the combined effects of overgrazing, deforestation, groundwater depletion, and shifting climate patterns. By the late 20th century, desertification was consuming Chinese farmland at a rate exceeding 3,400 square kilometers every single year. Sandstorms originating in the expanding desert regions were reaching Beijing with increasing frequency. The economic cost to agriculture was measured in tens of billions of yuan annually. And with a population approaching 1.4 billion people requiring food, the calculation was becoming desperate. The engineering response that China designed was not conceived as a single megaproject. It was a system, a coordinated network of water infrastructure, ecological intervention, and agricultural engineering that would take decades to build and generations to fully evaluate. Surveying teams entered the field years before construction began. Hydrological studies mapped aquifer systems at depths of hundreds of meters. River diversion feasibility studies modeled scenarios that previous generations of engineers would have considered unrealistic. And from all of this analysis, a construction program of historic ambition was assembled. The first machines to arrive at the reclamation sites were not the dramatic heavy equipment of major infrastructure projects. They were drilling rigs. Soil investigation teams moved across the target zones systematically, extracting core samples at hundreds of locations, building the underground picture that all subsequent engineering decisions would require. What the samples revealed was sobering. The surface soil in most target areas was severely degraded, fine organic particles stripped away by centuries of wind erosion, leaving behind coarse sand and gravel with almost no water retention capacity and minimal microbial life. But at depths of 1 to 3 meters in many locations, residual soil structure with measurable organic content remained. The soil was not dead, it was suppressed, and with the right engineering intervention, it could be rehabilitated. Site preparation began with road construction. Before any reclamation work could advance, access infrastructure had to be established across terrain that had no roads, no utilities, and no support facilities whatsoever. Bulldozers and graders pushed the first tracks across desert surfaces that had seen no heavy machinery before. Compaction equipment followed, creating the stable road bases that would carry the thousands of heavy truck movements that the coming construction required. Temporary accommodation camps were established at staging locations, self-contained communities with water supply, power generation, food service, and equipment maintenance facilities, housing workforces that at peak activity numbered in the tens of thousands. The canals came first. The fundamental logic was simple and unyielding. Without water, nothing else was possible. And in China's target reclamation zones, water was not available locally. It had to be brought from somewhere else entirely. The engineering solution was to redirect water from the wetter river systems of eastern and southern China through a network of engineered canals, tunnels, and pipeline corridors of massive scale. The largest of these water transfer corridors required excavation through terrain that alternated between loose sand, compacted clay, and solid rock. Excavators worked in continuous shifts, cutting the canal trench to specified dimensions, while dump trucks removed the excavated material to spoil areas alongside. In sandy terrain, temporary sheet piling or sloped excavation techniques were used to prevent trench wall collapse. In rock sections, controlled blasting was followed by mechanical excavation to reach the required profile. Once the trench was excavated to design dimensions, the concrete lining process began. Concrete pump trucks extended their booms into the canal channel, while workers directed the concrete flow onto prepared surfaces. Specialized canal lining formwork systems were used to achieve the precise cross-sectional profile required. Geomembrane liner sheets were placed beneath the concrete in sections with high groundwater tables to prevent seepage losses that would undermine the system's efficiency. Tunnel boring machines were deployed where the canal route passed through mountain ridges. These enormous rotating cutter head machines advanced through rock at rates of several meters per day, with workers immediately behind the cutting face installing precast concrete tunnel lining segments that would form the permanent channel structure. Ventilation, drainage, and construction support systems had to be managed simultaneously inside the tunnel environment as the boring machine advanced. Elevated aqueduct structures carried the water across valleys and dry riverbeds where surface canals were impractical. These structures required conventional bridge construction techniques adapted for water channel loads rather than traffic. Concrete pier foundations were drilled and cast, reinforcing steel cages were assembled and placed, and the water channel deck structure was cast in place in sequential segments working outward from each pier. Pumping stations were constructed at intervals along the canal route wherever gravity flow was insufficient to maintain the required water velocity against elevation. These industrial facilities housed multiple large centrifugal pumps driven by electric motors of significant power output. The construction of each pumping station involved reinforced concrete building structures, precision-installed pump and motor units, electrical switchgear and control systems, and the large-diameter inlet and outlet pipe connections that linked each station to the canal system. Simultaneously with the water infrastructure construction, the ecological stabilization program was advancing across the reclamation zones. This work began with the most fundamental challenge: stopping the sand from moving. Wind erosion control teams established straw checkerboard grid systems across target areas ahead of any planting or irrigation work. Workers installed bundles of wheat straw vertically into the sand surface in a precise grid pattern, creating barriers that reduced wind speed at ground level and caused wind-driven sand to deposit within the squares rather than continue moving. The installation was entirely manual, thousands of workers advancing in organized lines across the desert surface, methodically pushing straw into sand with purpose-built hand tools, creating the grid squares that would become the foundation for everything that followed. Within the stabilized grid squares, drought-tolerant pioneer plant species were introduced. Desert willow seedlings, saxaul tree saplings, and tamarisk cuttings were planted at measured intervals within each square. These first plantings were not agricultural crops, they were biological infrastructure, selected for their ability to survive in extreme conditions and their capacity to begin rebuilding soil structure through root development and organic matter contribution. As pioneer vegetation established over several growing seasons, the reclamation zones began to develop measurably different microclimate conditions at ground level. Wind speed across the surface dropped significantly, soil temperature fluctuations moderated, moisture retention in the upper soil horizon improved as root systems created pathways for water infiltration. The conditions for more demanding and productive plant species were slowly being created. The irrigation infrastructure that followed the ecological preparation phase was an engineering achievement of the first order. Drip irrigation networks, the most water-efficient irrigation technology commercially available, were deployed across the reclaimed zones at a scale unprecedented in agricultural history. Mechanical tubing installation equipment moved across prepared fields, laying parallel lines of polyethylene drip tubing at precise spacing intervals across the field surface at specified points. Along each tube, pressure-compensating emitters delivered precisely controlled water volumes directly to the root zone of the intended crop. The hydraulic design of these systems required thousands of individual calculations to ensure that water pressure at every emitter across fields covering hundreds of hectares remained within the tolerance required for consistent application. Filter stations at each field inlet protected the emitter orifices from the fine sediment that could cause blockage and system failure. Automated control valves managed the irrigation schedule for each field block, responding to soil moisture sensor data to deliver water when the crop required it and withhold it when soil moisture was sufficient. The soil amendment program that ran alongside irrigation installation introduced massive volumes of organic material to rehabilitate the degraded soil biology. Composted agricultural waste, biochar produced from crop residue combustion, and commercial microbial inoculant products were incorporated into the soil profile using deep tillage equipment before the first crop was planted. The quantities required were extraordinary. In some intensive reclamation zones, organic amendment applications exceeded several thousand tons per hectare over the first treatment cycle. The results that began appearing after the first water deliveries were documented by satellite imagery programs that tracked vegetation cover across the reclamation zones from orbit. The progression was initially slow and then increasingly dramatic. Isolated patches of green appearing in reclaimed areas grew into connected zones, then into continuous agricultural landscapes that expanded season by season as more reclamation frontier was brought under treatment. The Mu-Us sandy land along the border of Shanxi and Inner Mongolia, once one of China's most actively advancing deserts, was assessed by Chinese environmental authorities in 2020 as 93% restored. An area exceeding 42,000 square kilometers had been transformed from advancing desert to stabilized and partially productive land. The Kubuki Desert in Inner Mongolia had seen more than 6,000 square kilometers converted to productive use through the combined canal, drip irrigation, and ecological engineering systems. In Xinjiang, irrigated agricultural zones fed by the expanded canal infrastructure now produced cotton, tomatoes, grapes, and other crops across areas that a generation earlier had been unproductive desert. The impact on communities along the reclamation frontier has been profound. Agricultural families that had spent decades watching sand advance toward their homes and watching their fields diminish found themselves instead surrounded by expanding green. Crop yields improved dramatically with reliable irrigation. New crop varieties became viable that had never been possible in these locations before. Food processing facilities, cold storage logistics operations, and agricultural supply chain businesses emerged in communities that had previously supported only subsistence farming. The environmental effects extended far beyond the reclamation zones themselves. Sandstorm frequency affecting major northern Chinese cities declined measurably as the vegetation shelter belt networks interrupted the wind erosion processes that had generated these events. Air quality monitoring data from cities hundreds of kilometers from the reclamation frontiers documented significant improvements over the period of active reclamation work. River water quality downstream of reclaimed areas improved as bank erosion decreased and sedimentation loads reduced. The work has not stopped. Canal extensions continue to advance. Drip irrigation networks continue to expand. Ecological restoration programs continue planting, monitoring, and pushing the reclamation frontier further into territory that the desert previously held without contest. The engineering infrastructure that underpins the entire transformation, pumping, channeling, filtering, distributing, continues to operate around the clock every day in conditions that test machinery and human endurance to their limits. What China has demonstrated through this program is not simply that desert can be reclaimed, it is that the scale at which reclamation is attempted matters fundamentally. Single projects and isolated interventions cannot reverse desertification at the speed it advances, but a coordinated national engineering program sustained over decades, deploying the full range of hydrological, ecological, and agricultural engineering tools simultaneously, that can reverse the direction of an entire landscape. The desert is still there. It is ancient and powerful, and it has not surrendered. But the green line that marks the boundary of what engineering has reclaimed is still advancing, and the infrastructure that drives that advance grows more capable, more efficient, and more extensive with every passing year. In a century when feeding a growing global population from a shrinking base of productive soil has become one of civilization's defining engineering challenges, China's desert reclamation program stands as one of the most important proofs of concept in human history. The desert is not the end. It is the beginning of the next problem to solve. This is Quiet Tech Process.